Okay, so whenever you're talking about limits and continuity, there's a lot of things that fall into this. One of the first things that we learned how to do, other than just like generally finding a limit, which is not like something I can really put notes down for necessarily, was proving continuity at a point. So if f is continuous at, let's just call it like x equals a right here. So at whatever point, that might be x equals 2, x equals 0, whatever. So if f is continuous at a point, then f of a exists. There can be a lot of different ways this can be shown. If it's an equation, it means if you plug in 3 or a or whatever it is, that you get a number out. So like if it's natural log and you plug it in and it's a negative or something inside a natural log, then it doesn't exist at that point. So it could be plugging the number in. On the graph, it means that you've got a closed circle or continuous line. At x equals a, no holes, right? It can't be a hole. If you've got a hole at that point that's not filled in by a closed point, then f of a does not exist. The limit as x approaches a of f of x must exist. And so from the graph, this means that you have no holes, jumps, or vertical asymptotes. From an equation, especially like piecewise, I'm thinking like it's pretty much going from a piecewise equation, or technically any, but if they're asking you from an equation, it's almost always a piecewise. From a piecewise equation, you got to show that the limit as x approaches a from the right of f of x equals the limit as x approaches a from the left of f of x. Your limit from the left and the right have to be the same for that limit to exist at that point. And then the last thing that has to be true for the function to be continuous at that point is that f of a has to equal limit as x approaches a of f of x. This just means like if you had a hole, you have to have a closed-in circle to fill it in, right? You cannot have a hole. You can't have like not like this, like you got a hole in the graph and then a closed-in circle. This example right here meets the first two requirements. Actually, I should take holes off right here. Your limit can exist at a hole, but it's not going to be continuous. Meets first two requirements. but not the last. So continuity is something they sometimes ask about. You will definitely see in this section your limits as x approaches infinity, which can be asked in several different ways. So limits as x approaches infinity. These are used to find horizontal asymptotes. So you might have a question that doesn't ask you to do a limit, but asks you to find the horizontal asymptote. And to find the horizontal asymptote, you need to do the limit as x approaches infinity. And you need to use that notation, like if it's on a multiple choice, on a free response question, if it says find the horizontal asymptote, write limit as x approaches infinity of the function equals this to show your work for doing that. And, of course, limits as x approaches infinity, this is where we use one of our favorites. Webb was talking about it in the chess time today. Bobo, Botno, eats DC. So bigger on bottom 0, bigger on top not 1, and exponents are the same, divide coefficients. There. Okay, here. Your discontinuities are going to be under here, which is what I think some of you were asking about earlier. For discontinuities, you can have removable or non-removable. So non-removable, there are basically two types of non-removable that you can have. You can have a vertical asymptote, and a vertical asymptote would be something like this. For example, you've got x plus 2 over x minus 5 divided by x plus 3 right there. So for a vertical asymptote, it is a value that makes the denominator 0 and does not cancel with the top. So like you would have a vertical asymptote at x equals 3, negative 3 right there. And denominator is 0. Does not cancel. And the numerator The other type of non-removable that you might get would be a jump. And there's a couple examples of where you're going to get a jump in the graph. One example would be a piecewise that does not connect. So like to give a really simple example, it might be something like this. F of x equals x plus 2 for whenever x is greater than, I'm sorry, let's put less than on top. For when x is less than 3, and x minus 5 for when x is greater than or equal to 3. If I plug 3 in here, I get 5. If I plug 3 in here, I get negative 2. Those two are not the same value, so it doesn't meet up there. So that limit from the left and limit from the right don't match. The other example, and I think you guys had one on your practice test, are something like this. F of x equals 3x plus 2 over the absolute value of x plus 2. They love to put these on the test. Like there's, of the release stuff they've given out, it's on there a lot. If stuff cancels, almost, but there's absolute value bars, what's going to happen most of the time is that like the graph is going to look like this. It's going to be like a horizontal line until it gets here, and then it's going to jump up here like this. So that's going to be a jump in the graph. So that happens whenever stuff would cancel, but you've got absolute value bars. That's like a really specific example, but they love to throw it on there. So both of those would be jumps. Then you also can have removable discontinuities. Okay, and removable discontinuities, these are your holes. So your example for that would be like f of x equals x plus 2 over x minus 1 over x plus 2. Right. This would have a hole or removable discontinuity at x equals negative 2. And so it is whenever your denominator is 0 but cancels with the numerator there. Not all of these types of questions are on here, but intermediate value theorem was in this section. Let's do that one. And if we're thinking about the graph for intermediate value theorem, this is, we have like an A and a B here, and we got maybe from this point up to this point, and probably this graph there. And let's say this right here is C. It's just basically saying if we go from down here to up here, you got to cross the points that are in between those, right? What's your condition for intermediate value theorem? F is continuous. on A to B. So if you see it on free response, you got to say that F is continuous. And then the value, actually, it's going to be marked this way. That's going to be a C. This is going to be F of C. So it's going to be if F is continuous from A to B, and we're going to have F of A is less than F of C, which is less than F of B right here. So where I got that dotted line, that's like your middle value, wherever that's. So if they're saying, there were 7 fish in the pond and now there's 12 fish in the pond, were there ever 10 fish in the pond, right? That 10 is what goes in the middle, and you're just sandwiching that, so you're showing that one of these is lower, one of these is higher. It can be the other way around, like the B could be here and the A could be over here. So if that happens, then F of X, or F of, hold on, then there exists some value C on the interval A less than X less than B, such that F of X equals your F of C. So you got to equal that value somewhere. Keys to knowing its intermediate value theorem and not mean value theorem are that it should not talk about a derivative, and you should have, like, you're showing that I was at this low value, now I'm at this higher value, and so I had to cross that line in between somewhere. So